we have made it to the end of this unit on thermochemistry. And it wouldn't be right if we didn't also bring in a little equilibrium too, right? So here we're going to look at the relationship between free energy, Gibbs free energy, delta G, and equilibrium. Now, a few things that we've already mentioned. We have already mentioned that delta G equals 0 when a system is at equilibrium. And we've mentioned this little equation now that we can use delta G total would be the change in energy of the products minus reactants. For a reversible reaction, we want G to be 0. We want to be at equilibrium when delta G equals 0, which then would mean that the total energy of the products equals the total energy of the reactants. And then we know that the system is at equilibrium when G equals 0. Now, obviously, we can shift more forward or more reverse in a reversible reaction. Often that means by changing the temperature, and that might make G more positive or negative if I want it to favor a certain side of the reaction, more forward or more reverse. But if we are at equilibrium, G is 0. Now there is this cute little equation that we can use to compare delta G to the equilibrium position using our good old pal, the equilibrium constant. Yes, it's never going away, right? He's got to sneak his little head into every unit. So we're looking at delta G, the overall favorability of a reaction, equals opposite R. R is a constant. You'll look it up in your packet. Now, we used R back in the gas constant unit when we had perv-nert. In the packet, there are 3 versions of R. Now, at the time when we were doing gas laws, we said, don't use the one with joules because we use that for thermal. So there is a version of R in my packet. It looks like this, 8.314. In the packet, it's listed as like joule, mole, negative first, Kelvin, negative first. Or sometimes we just say like joules per mole Kelvin. That's the one you want for thermo. You want the version of R that uses joules. The other 2 are for perv-nert, and it is funky that they call it the gas constant, even though obviously here we don't have to use it for gases. But the other 2 versions of R have pressure in there. It's got like pressure in liters and like torr, atmospheres, millimeters mercury. Those are the ones that we want to use for gas laws. And then we just pick the right value of R depending on the pressure unit that we're given. But when we do thermo, then I want this one that's got joules in it. Now T is going to be my temperature, and it does need to be in Kelvin because R is in Kelvin. And then finally L and K. K is the equilibrium constant. Just our good old products over reactants equilibrium constant, natural log of K. And so again, it's a very simple equation to use. It's in the packet. They tell you what the variables stand for. It's plug and chug. We're more concerned with the outcome. How do delta G and K play with each other? So let's take a peek. Eventually, there's going to be 3 outcomes of this little equation. Delta G could be at 0, which would be fine. If G is 0, then the system is at equilibrium. Game on. Which would then mean that like energy of the products equals energy of the reactants. Because normally we would go products minus reactants. And so here, if G is 0, then those two values must be the same. And the system is at equilibrium. Now my other options, obviously G can be negative, and we know that if G is negative, the reaction is favorable, it's going forward, it's making products. Okay, so yeah, I mean here it says the system will shift forward to produce more products and eventually maybe achieve equilibrium. Well, you can kind of think of it in terms of this little equation too, that if G is negative, then it must mean that there's more product, I should say reactant, hello, that the energy value of the reactants is greater than that of the products. But eventually, if I want to reach equilibrium, I want these two to be equal. So I want less reactant, more product, until I get to a point where the energy of the products equals the energy level of the reactants. Then I am at equilibrium. So if the energy level of the reactants is too large, then we're going to shift forward. And we're going to try to shift forward and make more product. If G is positive, we know that the change is not favorable. Well, yeah, it's not favorable, or it's not going forward. It's not making products. We're favoring the reverse. We're favoring the reactants. Well, yeah, because now if I look at this and I say, okay, so if this is positive, then it must mean that the energy level of the products is larger than that of the reactants. So if I want to reach equilibrium and I want G to be 0, then I need to increase the energy level of my reactants, which means that, yeah, I'd have to go in reverse. Let's try this. Let's see what it's going to look like. This is one of my favorite problems ever. Okay, so this is the reaction for the corrosion of iron by oxygen. There's so much good chemistry. Like almost everything you need to know about thermochemistry is in this one problem. It's going to be so fantastic. We've got the balanced equation, and we want to use this data to calculate the equilibrium constant. Okay, well, if I eventually want to calculate the equilibrium constant, then it means that I want this equation. Delta G equals opposite R, T, L, and K. And I can solve for the equilibrium constant. I know the temperature. I know R, that's in my packet. But I need delta G. Actually, that's fine. We can calculate delta G. I'll calculate delta G as delta H minus temperature times delta S. But I'm going to need to calculate delta H and delta S. Oh, brother. All right, let's get to work, huh? Okay, let's go delta H. Delta H, products minus reactants. So my products will be 2 times that iron oxide, negative 826. I'll leave out the 0.0 and I'll leave out the units. I'll put them in at the end. Minus, now technically it's going to be 4 times 0 plus 3 times 0, because solid iron and oxygen gas are elements in their elemental state. So that doesn't shock me at all. And sometimes they might not even give me those zeros. But I would know that the heat of formation of a pure element in its elemental state is 0. So I've just got 2 times negative 826, or negative 1652. And this would come out in kilojoules then, because my delta H is in kilojoules. Now I can see it, like, does this make sense? It's exothermic. It's exothermic, but yeah, again, that makes sense. It's a synthesis. And synthesis reactions involve the forming of new bonds, which then should mean that energy is released. Yeah, this makes sense. It's exothermic. All All right, moving on to delta S. Delta S, 2 times my product, iron oxide, 90. That's my only product, minus 4 times the iron, 27, and 3 times the oxygen, 205. All right, so plug all this in, and this time my final answer is going to come out in joules. All righty, so let's see, what do we get here? Negative 543, and that's in joules. Or I could say joules per mole Kelvin. And then I say, does this make sense? Well, yeah, actually it does. This would mean a decrease in disorder. And yeah, that makes sense. I'm going from, 7 moles down to 2 moles. I'm going from gas down to all solid. I'm losing all my crazy gas particles. So yeah, just by looking at the components of the balanced equation, totally makes sense that there's a decrease in disorder. And notice too, like even when I look at the individual entropy values, notice that the 2 solids are pretty low, and then that oxygen gas is much higher. Well, yeah, the gas should be a lot more disorderly. Alrighty, so now it's time to plug this in. Delta G. Let's do it. Delta G is delta H, negative 1652, that's in kilojoules, minus temperature, but it's got to be in Kelvin. So this 25 degrees, I'm going to have to add my 273, which is in the packet. 298 Kelvin times, all right, so again, I run into this situation where I've got 2 different thermo units. I've got joules and kilojoules. I need them to be the same, and I already wrote down kilojoules, so I guess I'm just going to switch my entropy also to kilojoules. So let's make that negative 0.543 kilojoules. I could say kilojoules, or technically kilojoules per mole Kelvin. This would be like kilojoules per mole, if I want to write it that way. So again, my Kelvin units will cancel, and I'll have kilojoules per mole minus kilojoules per mole. So we plug all this in. These calculations are refreshing, right? Like the equations for the most part are plug and chug. I got to use a couple different equations, but they're all given to me in the packet. And again, most of the time I'm looking at the outcome in terms of the sign of the delta H, the delta S, the delta G. I mean, the numerical value is fine too. But yeah, like so far these have made sense. Now I do have opposing forces. I have an exothermic reaction, but it does have a decrease in entropy at 25 degrees. Oh, we're fine. Negative 1490, which would mean this is thermodynamically favorable. And in fact, it is thermodynamically favorable. And even though I have opposing forces, we would say that it's driven by enthalpy. You might see that term on like a free response. They might say, like, what is the driving force behind this reaction? And they'll bring up this term when you've got opposing delta H and delta S values. That, well, delta H is exothermic, that should be favorable, but delta S is not favorable. So if G is overall still negative, it must be the fact that it was so exothermic that when I compare these two in the same units, yeah, delta S is negative, but it's really small compared to the ginormous value we get for delta H, like negative 1,600 versus negative 0.54. So the exothermic value wins. That's the driving force that makes delta G overall still negative. All right, so now I can calculate the equilibrium constant, right? I might need a little more room, but I think I can do it. Okay, so let's see what we got here. We've got our delta G. Now, one thing I'm gonna have to just worry about, delta G is opposite RT, L, and K. Eventually, when I use R, so R is in the packet as 8.314 joules per mole Kelvin, or like mole to the negative first, Kelvin to the negative first. It's in joules. So I just calculated delta G in kilojoules, which I usually do because I figure if I'm going to use joules, it's going to be like giant numbers. And now I actually kind of need it back in joules to match the version of R that's given to me. Now, obviously, I could also change R into kilojoules, or I could say that G is negative 1,490,000 joules. I could do that. I mean, not a big deal. And it's just a really big number, but it's fine. So I gotta make sure that these guys match now. All right, then my temperature needs to be in Kelvin, so 298 Kelvin, and then I got natural log of K. So we're gonna try to simplify this the best we can. We're gonna do some algebra. So I'll take my negative 1,490,000, divide by negative 8.314, and divide by 298. All right, so then I'm looking at 601 equals L and K. And now to get rid of the natural log, when was the last time you hit the e to the x button on your calculator, right? Sounds kind of fun. So now I can say that K equals e to the 601st power, which if I plug that in my calculator, I get an error. Great. Okay, I get an error. So what if I just try something here? What if I go e to the 201st power? Okay, so I get a value for that. Let's say where is the limit on my calculator? Can I go e to the 401st power? Nope. Okay, what about e to the 301st power? Nope. Can I go e to the 300? Nope. Okay, so I'm running into a roadblock here, and that my calculator is saying an error overflow. I can do e to the 201st power, and that is about 2 times 10 to the 87th power, which obviously means then that e to the 600th power is going to be way bigger than 10 to the 87th power, which even that is a ridiculously high number. So my calculator is giving me an error, and maybe we can just say that K is huge. K is ginormous. It's so big it doesn't fit in my calculator. K is going to be bigger than 10 to the 87th power. Now again, this is an equilibrium constant, so K is a ratio of product over reactant. And so in this case, when K is ginormous, we don't even get a value because it's so huge, it must mean that we are favoring the forward big time. We are favoring the products big time. And in fact, we would usually say that when K is large, and this K is obviously beyond large, we would essentially say that this reaction goes to completion. Like, this isn't even something that we would consider to be a reversible reaction. Well, think about what the reaction was in the first place. It was the corrosion of iron to form iron oxide or rust. Well, they've got it written with a double-sided arrow, which is kind of silly, that this should really be a one-sided arrow. Think about like a rusty car. Is there anything you can do to turn that rust back into shiny iron? Not really. That it is so far forward that this reaction goes to completion. Iron reacts with oxygen to form rust. End of story. Done deal. Reaction is done. Rust then does not, in nature, have a tendency to go back and form iron and oxygen. This is really just a one-sided reaction. The K value is huge.